Welcome to volume part 2. So yesterday or last class, we did volume using rotations. So real quick, let's kind of review that concept. So let's say, remember we started out with these vases that we had yesterday, and then we essentially like created a function on the side of each one, and then we rotated it about an axis, okay? And that created, well, we rotated this area right here around an axis, and then that created this three-dimensional shape, and then from that three-dimensional shape we could find volume. So that was all volume by revolution. Today we're talking about something else called volume by cross sections. Okay, so you still want to imagine the shape that we have here. Like for example, this particular, either one of these vases, let's say I still had my axis here, okay, because that's where I would have rotated it. If I were to take a cross section, which means I just like, cut my vase in different places, I want to look at the flat shape that I would have as a result. And for this entire vase, both sides, no matter where I'm at in my vase, top, bottom, middle, wherever, if I were to do a cross section, each little bitty section would create, each flat surface would be a perfect circle, okay? And I would have to find the radius of the circle by knowing how far or what the function was and what my x value was for that function, okay? So today we're going to do something a little bit different. Instead of having perfect circles as our cross sections, we're going to start off with different shapes. The first one we're going to think about is a square. And to kind of help you guys with a visual, you are actually going to create this on your own, okay? You're going to create this 3D figure from a two-dimensional function. Okay, so the sub in the room is going to have all the supplies that you need. You're going to need some graph paper, some cardstock, some scissors. Be careful, don't run with those. Glue stick or tape, and a ruler. Okay, and what you're going to do on your piece of paper, okay, on your graph paper, you are going to sketch a region in quadrant 1 that is bounded above by the curve y equals the square root of x over the interval just from 0 to 4. Okay, so you might want to make it big enough so that way it's not super small and you can see the whole thing. Okay, and to create this 3D figure, you're going to quote like stack squares on top of your region. And I say stack them, they're not really going to be stacked, they're going to be taped or glued to your piece of paper. You're going to use 8 different squares that are equally spaced out. And so if you're going to start at 0 and go up to 4, I'll let you do the math and figure out how far apart they need to be. And then each one of those squares, you're going to want to have a little lip on each side so that you can actually like glue it to your paper. Let me show you an example real quick. The sub has one at the front of the room for you guys to look at, but I also have some pictures here. So these squares right here are going to come off your paper, but you can't really just put a square on paper without some way to adhere it. So that's what this little lip is. This lip right here, though, does not come from the actual square itself. So essentially you have a rectangular shape, but after you fold it, so you have this lip right here, this remaining piece that's sticking up off of your paper should be a perfect square. Now the question is, well, how do I find the height of the square? Well, if you look at these, the height of your square is dependent on where your x value is as you go down. So notice these squares are going to be a lot smaller than the squares on the back end. Does that make sense? Okay, so pause the video, take some time, build this little model. Okay, you can use the examples that I have at the front of the room to help you out, but you are going to create your own or your own three-dimensional shape using cross sections. And in this particular case, we are using squares. And the reason they're called square cross sections is because, quite simply, if you were to just cut, like let's say this had been a solid figure, if you were to just cut this right here, you would see that the flat surface that is created would be a perfect square. Okay, so again, pause it, create your own, come back when you're done. All right, so let's assume that you've done that and you've already created your square. Okay, what if we had used a different shape instead of a square? Like how would that affect the overall shape of your figure? So here we've got this cool little, we've got the square root curve, but then we have, like the corners kind of form their own cool little design. Okay, I want you to think about how different would this look if we had used a different shape. Like here we used squares. What if we had used circles? So if I had made each one of these semicircles instead, I can't really draw that well, but you get the idea. Let's say I had semicircles, okay? It would look a little bit different. Or I could have done equilateral triangles as my base, okay? Think about how that whole shape would look if I had done equilateral triangles, okay? So it would have looked a little bit differently. If I were to look at it from a bird's eye view, your square root function would still be visible, but the things that are coming off the page would look a little bit different. Like if you had the semicircles, it would be a big rounded shape, as opposed to the triangles, it would have like this one point kind of going through the middle, okay? So what are some buildings in real life that could actually take shape using cross sections? Can you think of any? Might take you a second. I usually have an example of one. Oh, it's hard to find it in my classroom, but it's up on the shelf here. You can't really see it. I've got a better picture of it here. Here are some different buildings that have cross sections in them. Okay, so you've got the Kauffman Center for Performing Arts in Kansas City. These are kind of rounded cross sections, you would say. They're not perfect circles. They're round on this side, but then they're flat on this other side. That's kind of a cool cross section. Okay, you've got the Burj Al Arab in Dubai. If you were to look at this from the top view, it's actually like two sides of a square, and then this part right here is rounded. It's actually a pretty cool building. Okay. And then you've got the Louvre in France, the museum. If you look at, I mean, obviously all of this back here is the museum itself, but let's look at this guy right here, the pyramid. The base of your pyramid is a perfect square, but if we were to do cross sections vertically along here, all of the cross sections would be triangles, okay? So this is the idea of volume by cross sections. Is essentially we're taking all of these different cross sections and we're adding them together, okay? So let's just talk about the area of the region in the plane. So again, we have the region of square root of x. Now this software system, I can only get it to graph up to 2, but just pretend that this number right here is a 4. Okay, you can pretend that. All right, cool. So if I wanted to find the area of the region, okay, now that's basically just, you know, I'll pretend it goes to 4. Oh, it's not going to stop. Hang on. I want it to go all the way. Yeah, that would be the, oh, ignore this stuff. I forgot. I took a different function and I modified it to the function that we want. So basically, if I wanted to find the area, yes, I would do the integral. But for our particular function, since we want to go from 0 to 4, our area is going to be the integral from 0 to 4 of the square root of x dx, right? Does everybody remember how to find area? Hopefully. I feel like that's a thing we should know by now. Okay. So then, quite simply, this becomes 2/3 x to the 3/2 from 0 to 4. I plug in 4 and 0, so 2/3 times 4 to the 3/2 minus 0. 4 to the 3/2 is, let's see, 8. Correct? Yeah, because square root of 4 is 2, then cubed is 8, times 2/3, so I have 16/3. So that is the region, or that is the area of the region of the square root of x just from 0 to 4. Okay, well, what if I wanted to know the area of just one of the squares of our cross section? So going back to the shape we created, I want to find the area of just like this square right here. Now, question, would that have the same area as this square right next to it, or this square, or any of the other squares? In this particular function, no, it would not, because none of your x values, none of your y values repeat, okay? The side lengths of your square is dependent on what your x value is as it gets plugged into your function. So because none of my y values are going to repeat, all of these squares are going to be are going to have a different side length, and therefore they're going to have a different area. Okay, so going back to how do we find the area of just one of our squares? Well, area is equal to side squared, and the length of one side is the square root of x squared. So then it's just x. So whatever our x value is, that's the area of each individual square. So this guy right here, we graphed it this is at 4. Okay, so the area of this square is 4. The area of this square is 3, 2, 1, 1, all of those. Okay, it's just your x value. That's not going to be true for all functions. That worked out for this one, okay? So then how could we find the volume of the 3D object that we ourselves created? So, but let's say that we could take each square that we've created, and now our squares are flat, right? Like they're pretty thin, okay? But let's imagine that the square itself that we've created, let's go back to it real quick. Let's imagine that I could fill in all of the area, like I could take this square right here and fill in all of the area up to the point before that with this square. So I would have, oh, that's, I would have this solid shape right here. Well, then I'd have another solid shape next to it that's a little bit bigger, okay? So I have all of these solid squares. This is a horrible drawing that I've just destroyed, but you know what? I'm hoping that you get the idea here. Let's erase all of this nonsense. Okay. Basically, I want you to envision that with each individual square, I could fill in all of that space back to the next square. I could take this square and fill in all the space back to that square. Okay, so each square in itself would have its own volume. And the volume, remember, volume of a square prism would be area of the base times the height. Well, the base would be the square, and the height would be the distance back to 0. Now, I think I'm realizing on this one that they're not perfectly spaced out. They should be spaced out about like 0.5 between each one, okay? This person didn't quite get that, but that's okay. It's fine. Yours is going to be perfect. I have no doubt. So each individual square that we have, okay, and we have a total of 8 of them. All right, so we're going to take the area of each one and we're going to multiply it by a height, and the height for all of them is going to be 0.5 because that's the distance between all of our individual squares, okay? But I have 8 of them and I'm going to add them all together. So when I have to add a bunch of things, we like to do a summation. So the overall volume is going to be equal to the sum from 1 to 8 of our individual squares, which the height of each square we've already talked about, or the area of each square was square root of x squared times the height in between each one, so 0.5, okay? And I should have an I right here. X sub I squared times 0.5, okay? So that's going to represent each individual square times the height, so that way it creates a 3-dimensional volume for each one, but I have 8 of them, so I add them all together, okay? So essentially this becomes 0.5 times, your first one would be 0.5 plus 1 plus 1.5, all the way up to 4, and you would end up with a volume of 9. So the volume of the 3-dimensional shape that we have created using our cross sections, okay, is 9. Now let's kind of tweak this a little bit and think about, well, what if I was able to find the volume assuming that I was able to have an infinite number of those squares, okay? So like, let's say I took as many squares as I possibly could and I just stacked them one after another. Well, when you do that, let me see if I can give you a visual here, okay? Let me hit reset. So if I did volume by squares, this is going to kind of give you a side view here. Let's say I could take an infinite number of squares and stack them all together. So my squares get bigger as I go through. Yeah, so I have this shape that's created by these squares right here. Do you guys see that? That cool little 3-dimensional shape is kind of rotating. Again, ignore this function. That's for a different problem, okay? This is the correct function that we want, okay? So what we're trying to do is we're trying to find the volume assuming that we were able to do this many squares, okay? Well, I had 8 squares before. Now I want an infinite number of them. So that means I'm going to take the limit as n approaches infinity, I equals 1 to n of square root of x sub I. Now instead of 0.5, I'm going to put a delta x right here because as I increase my number of squares, that's going to affect how close the squares are. So I'm going to call that delta x. And hopefully this whole process seems very familiar to you. Okay, this is the same process that we had when we went from a Riemann sum into an integral. And essentially we do have a Riemann sum here because I have my delta x and my limit as n approaches infinity. So then this turns into the integral from a to b of the square root of x dx. Okay, now specifically for the function that we have right here, we're going to use a and b as 0 to 4 square root of x. Oh, I forgot the squared. I'm so sorry. That should have been squared. Oh, squared. That was confusing. My bad. Okay, let me go back for a second. Okay, limit as n approaches infinity of the sum from I equals 1 to n, because I have an infinite number of squares. The area of each square is the square root of x squared, not just the square root of x like I had a second ago. Okay, so there should have been a squared there. There should be a squared there. There's a squared there with dx. That works out much better. Okay, because then this just turns into the integral from 0 to 4 of x with respect to x. So x squared over 2 from 0 to 4. I have 4 squared over 2 minus 0, and this just becomes 8. So if I were to have the volume using the 8 cross sections that I had earlier, my volume is 9. But if I were to make it a lot more accurate by having an infinite number of squares stacked end to end to end to end to end, by basically stacking a bunch of two-dimensional shapes together, I end up with a volume of 8. I think that's pretty cool. Okay, I hope you do, but hey, to each their own. So how could we kind of like write this whole process into a formula? If we were doing volume by square cross sections, okay, the formula is going to be the integral from a to b, whatever your function is, squared with respect to x. Now, this is only for a square cross section, and this is whenever this particular formula works when our cross sections are perpendicular to the x-axis. Okay, how would this be different if we had our cross sections perpendicular to the y-axis? Well, if our cross sections are perpendicular to the y-axis, now you're going to do everything. So this was volume in terms of x. Here, I'll kind of make this, let's do volume in terms of y. Everything would be in terms of y. So you'd go from a to b, but now your a to b would be your two y values where you start and finish. Your function in terms of y squared with respect to y. Okay, so it just depends on which direction your cross sections are going. Are they perpendicular to the x-axis or are they perpendicular to the y-axis? So you might want to make sure you're very, very careful about which one you're doing each time. Okay, so that was the formula for just a square. But remember a minute ago I told you, like, well, what if we didn't use squares? Okay, what if we had used semicircles instead? All right, so let's go back. Well, let's see. So here I have this nice square. What if instead I had a semicircle? This, right? Well, semicircle right here. What if I want you to visualize that this had been a semicircle? I can't really change that on this software, but I want you to visualize having a semicircle right here. Let me try something. Let's see, dude. Semicircle. Okay, it should go all, oh, that's so bad. My circle drawing skills are not quite as cool. There we go. That's pretty good. Okay, so remember, this distance right here is f of x. Okay, well, to find the area of a semicircle, that's half of a circle. So pi r squared over 2. Okay, but where in this case are we getting our radius? The entire function itself would be your diameter. So then my radius is going to be my function over 2. Does everybody see that? So remember, to find the area of a semicircle, it's half the area of a circle. Area of a circle is pi r squared. The distance from here to here is a radius, or is your radius. Well, this entire distance is my diameter, which is the same as my function. So half of that would be my radius. So f of x over 2 would be my radius. Okay, so going back to our flip chart here. Okay, so the area of a semicircle, again, was pi r squared over 2. So then the volume, let's do it in terms of x. We'll assume for a second that all of these are perpendicular to the x-axis. Okay, it's going to be from a to b, pi, my function, f of x, over 2 squared. Okay, and then I actually want half of this, so pi over 2 is what I should say. All right, so remember, my radius, this right here is your radius. It's half of your function. All that's being squared. And then pi r squared is a circle, but I want half of it because it's a semicircle. So dx. And we'll typically clean this up a lot of times and make this, let's say we could do first a to b pi over 2 times f of x. That's not what I want to write. Hang on. Let's do this. Let's try it a different way. Let's go. Pi over 2 a to b f of x, that by itself is squared, over 4 dx, because 2 squared is 4. But then if I wanted to, I could clean this up a little bit further and make this pi over 8 from a to b f of x squared dx. So now it looks a lot like the same formula that we had for a square, but instead of having it just f of x squared, we have a constant multiple out front of pi over 8 to represent that we are looking at a semicircle instead of a square. Okay, well, what if we had done equilateral triangles? Okay, so again, let's have a visual here. Let's go back to this. So this was with circles, but now let's say we wanted to do this with equilateral triangles. So here's the base of my triangle, and then it might not look like it's drawn a scale here, but my triangle, all the sides are going to be exactly the same. Okay, and so then I'd have all these triangles as they go back. So I've got an equilateral triangle. Here we go. And what we know so far is that the base, this distance, is f of x. Okay? Now, let's talk about the area of a triangle in general. The area of a triangle is 1/2 base times height. Okay? So the base in this case is now f of x. So 1/2 f of x. But now I need to figure out, well, what is my height? This is where your geometry / pre-cal knowledge comes back into play from equilateral triangles. We have a 30, 60, 90 special, right? So this is 60 degrees, 30 degrees, 90 degrees. Okay, if this is f of x, this is f of x, that's f of x, that's very well and good, but I need this guy right here. I need the height. Okay, well, we know that this little piece right here is f of x over 2. It's half of the base. Okay, and then since this side length is opposite the 60-degree angle, this side length is always the shortest side times √3. Okay, so then the height is going to be f of x over 2 times √3. Okay, this right here is my base. This guy right here is my height. If you don't remember that, I need you to go back and look up your special right triangle rules. Okay, if you're confused as to how that works, go back and look at those. Okay, but basically, so the area of our triangle now is all this fun stuff. 1/2 base times height. Well, 1/2, the base was f of x. The height is √3 over 2 times f of x. So then my volume in terms of x is going to be the area, the integral from a to b Again, the problem we had earlier was from 0 to 4. It's going to be different every time. I've got 1/2. My base was f of x. My height was root 3 over 2 f of x dx. Let's see if we can clean all this up. So 1/2 and root 3 over 2, I can bring both of those out, make that root 3 over 4 from a to b. And I've got f of x squared dx. Okay, so if you wanted to every time, you could work this whole thing out, or you can have these memorized. Like, these are common formulas, like semicircles and equilateral triangles are very common cross sections that we will use. So you can memorize those if you want to figure out how to find volume. Okay, let's just say we had a rectangle. Like your cross sections were rectangles whose height is 3 times the length of its base. Okay, so again, if I were to think of that triangle was along the base. So now I have this rectangle. Okay, f of x is like the base is f of x, but now the height of my rectangle is 3 times whatever my base was. So 3 f of x. Okay, well then the area is just base times height. It's going to be 3 times f of x squared. Okay, so then the volume is going to be from a to b, f of x, so that's your base, times 3 times f of x dx. So then it would be 3 a to b f of x squared with respect to x. Now that was just this particular problem with we wanted it 3 times the length of the base. They could change the number. They could have 5 times, 4 times, 10 times the length of the base. It's going to depend every time. Okay, but these are 3 pretty common ones. All right. Now let's try something a little bit trickier here. Let's say for the same function, the square root of x, and this, the same region from 0 to 4, find volume using the trapezoidal cross sections whose heights are half the base, and the top of each trapezoid is also half the base. Okay, so essentially, let's visualize this here. Okay, I've got a trapezoid along the base of the region. So this is f of x. Okay. The height of my trapezoid is half the base. So that's f of x over 2. And then the top base, I can't draw it that well, but that is also f of x over 2. Okay? So that's a beautiful trapezoid, by the way. I'm so proud of myself. The area of a trapezoid in general is 1/2 base 1 plus base 2 times your height. Okay, so let's plug in the things that we know here. In this case, 1/2 base 1, I'll go with the bottom base, so f of x plus base 2, the top one, f of x over 2 times your height, f of x over 2. Ooh, that's a mouthful. But do we understand how that worked? Okay, so we're going to take all of this. Oops, volume, I don't need to write that whole thing out. Volume is going to be the integral from a to b, 1/2 f of x over 2, and then times f of x over 2 dx. Remember, base 1, base 2, height. All right. So here we could clean this up. Oh, we want specifically our region from 0 to 4 of the square root of x. I'm going to go ahead and try to clean this up first. So I'm going to have a to b. I'm going to take, well, leave the 1/2 there for now. I'm going to go ahead and distribute this f of x. So I'm going to have f of x squared over 2 plus f of x squared over 4 dx. Everybody see where I'm going with that so far? Okay. And then I could distribute the 1/2, so I'd have a 1/4 and a 1/8 right here, or I could take out the 1/2. You could do this either way. I'll go ahead and distribute it, but then I'm probably going to take it back out. squared over 4 squared over 8 dx. Okay, so this is what I've got so far. All right, well, my original function, though, was the square root of x. So 0 to 4 root x squared over 4 plus root x squared over 8 dx. Okay, so this becomes, let's see, let me pause for just 1 second here. So I've got, okay, this works out really nicely. The squareds and the square roots cancel out. So 0 to 4, I have x over 4 plus x over 8 dx. I can just combine my fractions here. This is the same thing as 2 over 8. So this becomes, from 0 to 4, 3/8 x dx. That's not too shabby here. So then I do the reverse power rule on this bad boy, and I've got 3x squared, it's, well, x squared over 2 times 8, so 16 from 0 to 4. And this is going to be 3 times 4 squared over 16 minus 0. So this just becomes, 3. The volume of that was 3. So as crazy as that looked in the beginning, the volume is just 3. All right, so that is volume by cross sections. Okay, it's a little bit different than volume by rotation. So if you have any questions about this, please go to CalcChat, CalcView, Khan Academy, or Prof. Rob Bob. They have great videos explaining all these things. You can also ask questions of your neighbor if somebody understands it a little bit better than you do. But either way, use your resources.